Okay, I'm gonna start my timer so I can hopefully put this in for you guys. I gotta get my. Wow, you got a lot of questions. This is more questions than I had for the final exam last year, for either final exam. Okay, let's start my stopwatch so I can put in the time at which I answer the questions. I gotta get my testing thing. You're on a leg, and I want to check on my. Checking my eye thing. But if the video's working. Okay. Come on, thingy. And as long as that's working in there, I should be okay. I'm sorry what was running late. Those kids were not going to sleep. One would go to sleep, and then the other one would wake up, and blah, vice versa. So, okay, I'm working. The video's working. Okay, so I was going to organize everything, but then I thought, that's just a waste of time. I'm just going to go for it in the random order that's in there. Normally, it would look a little bit better because there wouldn't be so many questions, and I organize it beforehand. So I think in the next video, I'm going to have like categories that you guys can fill in, so that will make things a little bit better. Okay, I can do a screen share here so you can see kind of what I'm looking at. So okay, where I am for number 111 on page 167. I remember this question. And I think what's going on with this person is their calculator is malfunctioning on them. So I divided 211 times 10 to the negative 8th. 211 times 10 to the negative 8th by Planck's constant. Okay, so they got that 211 times 10 to the negative 8th by taking those two energy values and finding the difference between them, like literally subtracting them. 2 times 10 to the negative 20th minus, 6.05 times 10 to the negative 20th minus 2.18 times 10 to the negative 18, and you would get 10 to the negative 8. Let me do the math. Yeah, times 10 to the negative 20. Do you have my calculator? I think so. I'll do it again. Okay. So to this person who's in the question, if you can see what I'm changing here, this should be to the negative 18. So you're taking the two numbers that are in the textbook, the energy level values, and subtracting them. Let me see if I can show you a little better here. Paint. So in there you have, the different energy levels. I don't know how many I drew, but let's say this is n equals 6, the sixth energy level, down to n equals 1, the first energy level, the first ring or orbital. Energy level is better way to go, not orbital. So n equals 6 is 6.05 times 10 to the negative 20. And n equals 1, as according to the textbook, is negative 2.18 times 10 to the negative 18 joules. And so if I take the difference of these two, like subtract the two, that would be how much energy you get when you go from n equals 6 to n equals 1. That's how much energy it takes, those difference. I get 2.12 times 10 to the negative 18. And the person who was typing their question has only to the negative 8. So that might be your first problem. That's equal to E. And then I know that E is equal to H times nu, or frequency. So that means my E, my 2.12 times 10 to the negative 18, is equal to H, which is 6.626. That's awful. 6.626 times 10 to the negative 34 joules times 6 times frequency. So then I can find frequency by dividing both sides by H. And that's when I get negative 3.2 times 10 to the 15th. I believe, if I remember right, for this question, you're trying to find wavelength. So that's what I'm going to use the second equation, C equals frequency times wavelength. So my frequency is this, 3.2, 10 to the negative 15, or 10 to the positive 15, and my C is 3 times 10 to the 8th. And so if I divide 3 times 10 to the 8th by 3.2, 10 to the negative 10 to the positive 15, that's when I get the wavelength equal 9.4 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, negative 8. Wow, that's awful. 9.4 times 10 to the negative 8, and that would be in meters. So all in all, what I want to say to that person I am back on my screen so I can see what they said. They said they're getting 10 to the negative 43. The problem that you're probably doing is maybe you're not on the answer sheet. What you're probably doing wrong is using your calculator wrong. So what I mean is, like a lot of calculators, like I just have a ghetto calculator. So the ghetto calculator has times 10 to the, and I'm guessing that's what you're using is the times 10 to the button. And what you want to be using is the EE button. Now my calculator here doesn't have the EE button, but the EE button is really awesome. Like it literally has EE. So if you wanted to do the speed of light, 3 times 10 to the 8th, you would hit 3 and then the EE button 8. So your calculator says 3 big E 8. And that's telling the calculator 3 times 10 to the 8th. That's the button you want to use. That'll make your life a heck of a lot easier. And if you're confused at all with that, come and see me right before the test so I can show you where the button is on your calculator and how to put it in. If you use the EE button, you don't have to type in times 10 to the, because every time you do times 10 to the and put in a scientific notation, you need parentheses around it. And lots of times you'll be doing problems and you'll forget the parentheses. And that's how you got 10 to the negative 43, because you didn't put enough parentheses around your scientific notation number. So if you don't want to use the EE button, put in a lot of parentheses to keep your scientific notation numbers together. Here we go. If an atom is in ground state, would the electron configuration of the atom just follow the 3 rules? Yes. What if the atom is not in ground state? Will the electron configuration still be the same? It will not be the same. It will not follow the 3 rules. It won't be the same. It'll be in an outer energy level, so you'd have to know what energy level it's in to show where it's at. You could show a hypothetical electron configuration of an excited state. That would be taking something and just throwing it like in the 4F block or something like that. You won't be asked to do that, but that is the answer to that question. I'm not doing my timing. I answered that question around 8:23. Okay. So there are principal energy levels, and every principal energy level has energy sublevels. Yes. Does each energy sublevel have S, P, D, and F, or does it only start for the 4th principal energy level? Okay. Only the 4th energy level has S, P, D, and F. The first one has S. The second one has S and P, 2. The third one has S, P, and D, 1, 2, 3. The fourth one has S, P, D, and F, 1, 2, 3, 4. And if you did a 5th one, there would have S, P, D, F, and something. Now, we don't have enough elements that go past the F block to have that something, but maybe if we keep discovering elements, we will come up with that one, and they'll actually have to have something other than just the F block, but we don't have that at this time. For number 38 in chapter 6. I'm doing terrible on time. That's okay. I'll put this one in. 9:24. Number 30 in chapter 6. How do I know if it's a nonmetal? It says it discovered an element with 117 protons. So if it was 117 protons, oh gosh, can you even see this? If it was 117 protons, it would have to be located right below here in the halogen section. And in the halogen section, oh yeah, you would have to question if it was a nonmetal, metal, or metalloid. I would have to say it's a metalloid because it's right on the stair step. You can see the green one. This is the back cover here of your textbook. In the green spot, that's going to be a metalloid. It can be a little wishy-washy. They didn't make this a metalloid, so you don't know for sure, but I would have to say noble gas is going to be non-metal because all noble gases are, but I would make the best guess that this is a metalloid. So it's dependent on where it is around the stair step and how you know if it's a metal, non-metal, or metalloid. It's typing. The person who's typing right here, I'm going to come back to your question. I don't want to, oh, okay, you're getting rid of it. Okay, I'm going to keep moving downward. Here, I'll share my screen so you can see what the heck I'm doing. Okay. You don't want to see me anyway. Let's be real. Okay, moving along. I'm trying to, like I said, only doing the dark questions. Okay, we didn't know which ones are metals, non-metals, and metallites. You are going to be having my periodic table. So my periodic table doesn't have your coloring, but what it does have is a stair step. So you'll have to remember to the left of the stair step, that ziggy-zaggy line is going to be metals. To the right of the stair step is non-metals. And anything right along the stair step is going to be metalloid. I'm not going to pick a sneaky metalloid like, I don't know, they're just all but aluminum are metalloids. Boron is a non-metal usually. I'm not going to pick anything sneaky. So I hope that helps you there. 44. We end at 10:30? Heck no. I hope the video keeps going, otherwise I'll just make a new one. Okay, keep going downward. I'm trying to find an indented one. I believe you can see my screen. Okay, here we go. Does each atom have the same number? 1204. Does each atom have the same number of energy levels and just does not use all of them unless its electrons are excited? Does each atom have the same number of energy levels? No, because some energy levels go like into the 4f block and the 6s block, and some atoms only go into the 2s block. And just so they could, like, electrons can be excited into those energy levels, definitely. And there's like an unending level of energy levels really until you get to a point where you just completely kick the electron out of the atom. And that's what we've been talking about for ionization energy. So not every atom has the same number of energy levels, but there are empty spots where it could have the electron excite into that spot. There's no set number. Choose the next one. Can you go over the wave mechanical model, how the Heisenberg uncertainty principle and de Broglie equation support the model? Sure. Am I screen sharing? Yes. Okay. Okay. So the de Broglie equation is that fancy one where you have the wavelength and it's equal to, I think, h mv. Yes. So Planck's constant on top, and it's a really, really small number, and then we have the mass and the velocity on the bottom. And what the wavelength equation was, the de Broglie equation was really trying to tell you is that everything moves in waves. Electrons are things that moves in waves. And so he kind of did something new with the quantum mechanic model, where the idea that everything moves in waves, which was really revolutionary for the time. But most importantly, he was talking about electrons moving in waves, since we're talking about atoms. And if electrons move in waves, well, then suddenly they can, you know, create these kind of funny shapes, which make you think about the different shaped orbitals. So since electrons can move in waves, they're going to like move in waves through the orbitals, and that can create those clover shapes and all sorts of different things. So the idea that they move in waves supports the idea that you can have these funny looking shapes, and supports, yeah, that's all we're going to kind of sit at, that part. The Heisenberg uncertainty principle takes a look at the position as well as the velocity, and you can't know the position and the velocity of an electron at the same time. Like, you can't be 100% certain of the position and 100% certain of its velocity. That's impossible for an electron, because we can't see an electron. So the only way to see an electron, quote unquote see an electron, is to shoot it with something. It's kind of like my idea with the balloon. If you hit the balloon, then you've really changed the position of the balloon. So same thing with electron. If we want to see an electron, all we can do is shoot things at it and see where those things we shoot at comes out. But every time we shoot something at it and hit an electron, it's going to change where the electron is. So we can say we're like 50% positive of the position and 50% positive of its velocity of the electron, or change it to 40-60. But we can't ever know exactly position and exactly velocity. Because of that, we can't do Bohr's orbits, because that suggests we know exactly the path of the electron, but we don't. That's why we have to do the bubbles idea, where we know electrons live in this bubble somewhere. We just don't exactly know its path or where it is. And we can only know that it's in there most of the time. We don't know it's in there every single moment of every single day. Okay. What exactly did Schrodinger's equation prove? It did a lot of math that showed Schrodinger used math to prove the shape at which the electrons can live in. So he did the shape proving. Without his fancy math, his calculus, we couldn't know that the shape of the d orbitals are like those clover shapes in the donut without him. Can you go over the drawings that relate to electron? This was the Aufbau drawings. Okay. Okay, let's pick an element like, I don't know, magnesium. That sounds good. If I do electron configuration for magnesium, I get 1s2, 2s2, 2p6, 3s2. And so if I'm going to draw the Aufbau diagram, I'm going to have energy, and the arrow is pointing upwards because as you move up in energy, it's in a higher energy level. The lower energy levels are the lower parts. We start with 1s. I draw a line because I'm going to put 2 electrons on that spot. That covers my 1s2. Moving up, here's my 2s2. 2s has a line, it has 2 electrons, so I go 1 and 2. Moving up, I've got my 2p6. My p's I kind of do in a separate lane, 1, 2, 3. I know that I have 3 lines to do because it has a total of 6 electrons. 6 electrons, each line holds 2, so 6 divided by 2 makes 3. So 1, 2, 3, 4, 5, 6. You can also use your periodic table and see that the p block has 6 across. 6 is the total number of electrons we can fit, I should say. And then in the end, ooh, this is hard to fit. I've got my 3s here, and that goes 2 electrons on top there. If I happen to go into the D block, you put your D's over here. That is coming way above, so it's clearly not in this magnesium, but that's where you put it. So you notice I've got the row of S's, I got the row of P's, I got the row of D's, and if I had F's, I'd put them over here, and that's kind of how you do an Aufbau diagram from an electron configuration. So you don't really have to memorize all those boxes, you just have to know electron configurations, which I know you guys know how to do. You're really good at that. Oh. Okay. Do 9, well, let's put my time. Do 9 orbitals make up the 3rd energy level? If so, is this how it works for every energy level, that a set number of orbitals are part of it? Do 9 orbitals make up the 3rd level? Okay, let me see if I need a periodic table. It's this one, which looks just like ours. Okay, so if you take a look at this periodic table, the number of orbitals, so if you take, okay, so the first energy level has only a 1s, so you're going to have a 1 orbital, an s orbital. The second energy level has s's and p's, S orbital is one s orbital, and there are 3 shapes of the p, so that makes 3 orbitals of p. That's a total of 4 orbitals, 1 s and 3 p's. But also, and then that's the second energy level. I feel like I'm not answering the question. Let me reread it. I feel like I'm blabbing and it's not right. Do 9 orbitals make up the third energy level? Let me write stuff instead. Okay. So in the first energy level, you only have 1 s, and there are 2 electrons that live there. So that is 1 orbital, because it only is an S shape. In the second energy level, you have S's and P's. Now there is 1 S shape, and there happens to be 3 shapes of P's. That takes a total of 4 orbitals. Each orbital is a shape. So we have a sphere shape and 3 different clover shapes. Not clover, 3 different dumbbell shapes. In the third energy level, you have S, P, and D. There's only 1 S shape, there's 3 P shapes, and there happens to be 5 D shapes. That's why we draw 5 lines. So if we add those up, that's a total of 9 orbitals. Go into the fourth energy level, we have S, P, D, and F. S is 1, P is 3, D is 5, and F is 7, because it's 14 across. So if I add all those up, I get 9 plus 7 makes 16 orbitals. I think this answers that person's question. I'm going to say it does. So excellent. Let's see what my time is. We're at 21. We need to know how to predict what characteristics undiscovered elements would have, like in chapter 6 homework. The characteristics, you'd have to know if it's a metal or a non-metal, and then you would want to know, like metals are malleable, just the stuff that you have in the Venn diagram. Non-metals are not malleable, they're mostly gases. Metals are not gases, that kind of thing. The basic stuff that I had in the Venn diagram of what metals are. I'm kind of assuming that you kind of know what metals look like. Copper, that kind of stuff. Okay. Can you explain? Please tell. Can you please explain how to tell from the graph it's increasing or decreasing the graph with all the dots? Okay. Let's go to, you're like, go to the test folder, right? Yeah, I know. Oh, that's annoying to look at, isn't it? So, okay. Okay, so when I look at this, you can think of it one or two ways. So I might take a look at my periodic table. Now, hydrogen is kind of funky-dunky, so I'm going to start with probably number 3, lithium. So if I look for number 3, lithium, 1, 2, 3, lithium is right here. And then I'm going to move across the periodic table and go to number 4, beryllium. Number 4 is going up. I'll go to 5, which is boron. Keep going across the periodic table. 6 for carbon, 7 for nitrogen, 8 for oxygen, 9 for fluorine. So I can see as I went across the periodic table, I went upward. So across the periodic table, I went upward. That's the first thing you might want to do. You could also draw colors of lines, but you may not have time to draw colors of lines. So this is another way to look at it rather than looking at lines. Just take the periodic table and move yourself across, one dot to the next. When you have to go down a group, that's when I would also start with something like lithium, who's number 3. If I move down his group, I go to sodium, which is number 11. So 3, and then number 11 is down here. I went slightly down. Going to 19, it looks like I went slightly down. Moving to 37, it looks like I might have stayed the same or maybe gone slightly down. So this is a slightly down trend as we move across. So the way I like to think about reading the graphs, I like to start with lithium. He's number 3. Start with lithium, and then I go 4, 5, 6, 7 across the periodic table. That will get me across, and just see where I go when I think about 3, 4, 5, 6. And then I take a look at going down the period, or sorry, not down the period, down the group. So I just look at the alkali metals. I go for lithium, then down below him is sodium, potassium. So I look at 3, then 11, then 19. I hope that might be a different way, rather than using colors if the colors weren't working for you. Hopefully that will help. Okay. How do I do atoms get smaller on the left of the periodic table? They don't get smaller on the left of the periodic table. That's what concerned me with this one. So as you go to the right on the periodic table, they get smaller. They get right as you go on the smaller. They get smaller as you go right on the periodic table because of you're adding energy. You're not adding energy levels. Let me do a picture. You can't. It's hard to just listen to me. So, oh, that's my periodic table. Wow, that's awful. So, on this side of the periodic table, let's say you have one ring, and as you move to the right on the periodic table, that one ring comes in closer. So, as you move to the right of the periodic table, it energy levels. Notice I have one ring on the left, one ring on the right. Does not gain energy levels. It is gaining number of electrons. The number of electrons goes up, and the number of protons goes up. The number of electrons going up doesn't really matter because they just stay on that same ring. What does matter is the number of protons go up. Since you have lots and lots of protons, they're all stuck right in the center there, and all those protons are like super magnets, and they are stronger together than they are alone, just like the Power Rangers, and they can hold things in tighter. So it takes that ring of electrons and holds it in tighter because the protons are so much stronger when they're together than they are alone. Okay. Moving along, moving along. Can I please explain the different trends and how they differ? I don't know that I want to do that, to be honest. Like, and how they differ? We might come back to that. But I'll do one trend, but I'm not going to explain all of the trends. That's just, I think that we've done that in class a lot, and I just don't feel like doing that. I just don't think that that's what my review video's purpose is. Okay, so I'm probably not going to do that. Do we need to know? I hope that doesn't make me a big meanie butt. It might be, but I don't think so. Okay, do you need to know 26, 45? Do you know how to draw atoms based on electron configuration? If so, how do we do that? I think what they're talking about is the Aufbau diagram there. If you're not talking about the Aufbau diagram, then you're talking about something like the drawing of the circles and stuff. That's not anything fancy. Like, don't look for anything fancy. If you think about magnesium, magnesium is 1s2, 2s2, 2p6, 3s2. And for magnesium, come on. Like my 1s here, that'd be a small circle. My 2s would be a larger circle. My 2p is going to have these dumbbell shapes. There's 3 different kinds of dumbbell shapes. You can see it's not that great. My 3s is going to, oops, I'm doing it in blue, come on, or purple, is going to be even a larger circle. So really what you're going to see isn't this inner stuff. You're really just going to see that outer circle, that s orbital, that it always gets bigger as energy levels get bigger. So that would be a picture of my atom, this magnesium part. And if you can hear that, that's my little guy waking up again, because he is not the best sleeper in the world. I'm hoping he will calm down, but he probably won't. So, oh, Jacob. Why is the periodic table organized the way that it is? It's organized based on families or groups. In other words, like your family, you all kind of look the same. Like you're all Irish and you kind of all look like you're Irish. Or you're all really tall people and that's the way you are. Atoms are the same idea. All the noble gases are all nonmetals. They happen to have a really small atom by radius. They are they don't have an electronegativity. They have a very high ionization energy because they don't want to lose electrons. So the periodic table is organized in the way in which they are grouped by groups that are like them. Rutherford just add orbits to help better understand the modern atom. Rutherford did not or did orbits. Rutherford just thought electrons kind of zip around. Or was it Bohr who added to Thomson's model? It went Thomson first, then Rutherford, then Bohr. There you go. Does agree. Okay. No, he doesn't. de Broglie doesn't, his idea that it moves in waves doesn't control the shapes. Schrodinger proved the shapes. He was the one who did the fancy math that did the shapes. De Broglie's equation contributes the idea that things move in waves. And so if you remember from that model, that FET simulation, how things kind of move in and out, it kind of, by having things move in waves, it changes the idea that electron is a particle. A particle is a wave. And if you think about the wave mechanical model, wave is part of it. It's the idea that electrons move in waves, and so we can't know exactly where things are. It's the idea that electrons move in waves, so they don't follow set paths, because waves will move along different coordinates. So I think that's all more detail that I'm going to go into. What do 30 What do electron configurations tell us about the structure of the atom? It tells us what energy level they're in. It tells us the shape of the orbitals and how far away the electrons are from the atom. Yeah, I mean, electron configurations are the structure of the atom. The structure of the atom is having these different shape bubbles. It kind of tells us that there's a strong probability that you'll find electrons in this region, something closer to the nucleus. As you move outwards, it's less likely to find in there. So the structure of the atom is completely controlled by electron configuration, which tells you the shape of the orbitals, which tells you where the electrons might live, which tells you the shape of the atom. Can we go to the Rutherford portion? During Rutherford's Goldfloor experiment, the alpha particle hit something and bounced back from where it came. What did this piece of evidence tell Rutherford? It told them that he had to hit something that was really dense and positive. He shot alpha particles at a let's see if I can get you an image. Not of him. Yeah, this one's a good one. Okay. So when Rutherford did his Goldfloor experiment, he basically shot alpha particles at atoms. Now, most of the time they went right through, which means it went through the electron cloud and didn't even touch an electron because most of the atom is empty space. But sometimes, as you can see with the red line, sometimes the alpha particle hit something that was super dense. The only way it could come back is if a positive alpha particle hit something that was positive and it basically bounced it back. It deflected it. So the alpha particle hit something really dense and came back. Alpha particles are pretty big. So if you're going to block an alpha particle, you've got to be pretty big yourself. Big as in dense. The nucleus is dense. It's not big as in size, volume-wise. It is just really dense. I think that picture does a good job. Okay. Oh my God, am I getting to the bottom? Holy Annas. I feel like I'm going to miss something. If I miss something and you guys are looking at it and like, why hasn't she answered it yet? Just highlight it and I can see it better. Explain how electronegativity. I'm not going to do all the trends. I'm sorry, I just can't. I mean, that's part of your lab that's due, and I think we've talked about it a lot. I'm just going to be mean and say no. I'm not going to. I'm sorry. I kind of feel bad, but I kind of don't. Okay. Well, we have to memorize what Bohr did and what Rutherford did and what the other people did. No, I don't think you should have to memorize what he did. I mean, I think it's helpful to know if I could draw the picture of the different models. Like if I drew Thomson's a chocolate chip cookie. It moved from a chocolate chip cookie to the planetary model where electrons are zipping around to the idea of orbits to the wave mechanical model. I think that if you can draw those 4 pictures, you can really know a lot about what the atom is. And then, like I said, we're going to talk about claims and evidence. Like if we move up ahead here and take a look at my Rutherford question that I answered, this question right here, that's a typical question I might ask on the test. You can see I told you Rutherford, I told you about the gold foil experiment, I told you alpha particles, kind of gave you some hints into things. And I gave you this piece of evidence. It bounced back. What did that evidence tell you? That's the kind of idea that you're going to have to know. Oh, there's more. Okay. Okay. How can I describe the Heisenberg uncertainty principle in the Joule equation as well as this one I answered above. When did I answer that? If somebody just recently asked this, how can I describe them? I think I did a pretty good job in my thing. So I don't know. Can you ask more here? Like, did I not do a good job? I think that's all you need to know. Oh, okay. I'm coming back. I'm going to go up. You can see me in the video. Okay. To this highlighted one. Will we get a short answer? You won't get a rubric. There's, of course, going to be math on there, so you have to show your work. Other parts, I'm trying to think what other questions. I don't think you're going to really need a rubric because it's not like an essay. I mean, it's not really rubric worthy questions. Like a rubric to me should be used like when I give you like a big beefy essay. But I'm not giving you a beefy essay. It's like short answer. Like when you think of the flame test lab, how it was just like, you know, those short kind of questions. That's the kind of thing I'm going to ask in my short answer stuff. And I don't think the flame test lab had rubric worthy questions. It was like you got it right or you didn't. It wasn't a big essay. So I hope I helped with that one. And if you know what I mean, if you think that I should have more rubrics on my tests, I'm totally open to that. I don't think that my questions warrant that. But that person out there, if you think so after you take the test, please tell me. I mean, I'd love to know what you think. Where can I find the PowerPoint on this? 36. Where can I find the PowerPoint of the J.J. Thompson? Okay. So I know Rutherford is in the textbook. He's in chapter 4, if you want to read about him. I think it's a good read, you know. I'm even going to give you the page number. Rutherford starts on page 111. They do a really good job on that part. So I would read page 111. Oh. I do not have my PowerPoint on the J.J. Thompson and all that stuff because it was all pictures, so I didn't find that to be totally worthy. The articles were kind of good. I can look to see. I'm not opposed to putting it up. I just don't think it was super helpful. I don't like to put all my PowerPoints up because then you see where I'm going, and I want it to be kind of like, you know, it's like seeing the end of the movie. Nobody wants to see that. And here's my PowerPoint, but I don't think that it's going to be what you're looking for. So I'm not going to put it up there because it's not entirely what you're looking for. I think what you're looking for is what the textbook's going to give you. And that's why I'm not going to put my PowerPoint, because it's not going to be as good. What did Rutherford do to create those claims? He did a gold foil experiment. That's what we were seeing in the image here. Oh, look, they even have like observation interpretation, which is my version of evidence and claim. How about that? That's a pretty good little thing there. Hey, perfect. I'm going to copy that into there for you. And we did this, but it's lovely. Boom. What shape are the echo orbitals? They are funky shaped. I'm going to stop my screen sharing. You can see me. I'm going to go look through the document one more time and see how it's done, I think. Make sure I got something by everything. Box constant. did Heisenberg and Cerny principle talk about? What did it bring to the table? Time was it? We need to know the reason behind why electrons make a bigger jump as fluids. Remember when I did 1645. Oh, I got typos. That's cool. Okay, folks, I think that is the end. I did a pretty good job, I think. I typed a lot more answers than I normally do. But they seem typable because they were yeses and nos. I just didn't answer that, no. Person asks, so we essentially have to memorize the ways in which each scientist revised the model. I hope it doesn't feel like memorizing. I mean, I really think that if you know the picture of the atom, you can logically think through the rest of it. I try to give you a lot of stuff like in the question and say, I don't know, I guess you probably feel like it is. I'm sorry. I'm trying to just make you think about. It's going to feel as tough, I think, as the atomic theory review worksheet. So if that felt like you were just putting down things you memorized, then I guess yes. If it didn't feel like you were doing memorizing, you were kind of using logic as you were doing it, and you just kind of knew it, then I hope that's what it felt like. So I guess I am mean, and you do have to memorize it. I don't know. I don't think it's as much memorizing as bio, right? I don't teach bio. So I don't know. Oh boy, that's the end of the show. Whew. That's a doozy, folks. That's a doozy. I think this is the most views I've ever had. That's pretty awesome. You can always watch it later too. I mean, you don't have to watch it live. If you want to watch it live, then you can just like ask me questions and stuff if I confuse you. But you don't have to watch it live. You can watch it the next day or later tonight. But why don't you just go to bed? That's what I'm going to do. I'm going to hopefully go to bed. I'm going to go have like a bowl of cereal, like a small bowl of cereal, and go to bed. You might want to do that too. All right. I enjoyed our time. I hope I was helpful. And if you have any pointers like how I should do this differently or make it a little bit better, I'm totally up for it. Welcome to my little house here. This is, if you're wondering what's behind me over here, that's my cat likes to sit in the window, so I made a little thing for my cat to sit on. It's a lamp. That's my office. Okay. Have a good night.